Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one's the third in the series on dimensional analysis, and it focuses on the use of dimensional consistency arguments to establish the indices in a proposed formula. Let's just briefly remind ourselves the three dimensional concepts that are at work in this analysis. The first is mass measured in kilograms, the second is length measured in meters, and the third is time measured in seconds. Now if we're going to propose a formula to relate physical characteristics, physical measurements to some property, then the first thing to do is to brainstorm what physical characteristics, physical measurements, physical concepts could contribute. And in this case, the problem we're going to look at is determining the velocity of a wave in deep water. What factors could contribute to that velocity v meters per second squared? Well, we might speculate that the density of the water ρ would contribute. The wavelength lambda would contribute. The acceleration due to gravity would contribute. When I say contribute, we're saying that we expect that the resulting velocity to be dependent in some measure on those different characteristics. So we've expressed that dependence by putting in the three factors ρ, g and lambda with unknown indices alpha, beta and gamma. And in addition, there's a dimensional constant so that we can actually write equals, since we've no right to assume that it would just be a product with a factor 1 in front. Now we're going to use dimensional analysis on that formula to work out what those indices are going to be. Well, we begin, if it's dimensional analysis, by looking at the various factors and what their dimensions would be. So for velocity itself, we have, as usual, that's meant to be an L, Lt to the minus 1. We have, for density, we have mass over volume, so ml to the minus 3. Acceleration due to gravity, acceleration, so Lt to the minus 2. And the wavelength is just a length, so L. So using those four different formulae, we can feed into the one that we've got. So hence what we have on dimensional analysis, the V becomes its dimensions Lt to the minus 1, the ρ becomes ml to the minus 3, and so on for the other two factors. Now, since we have three dimensions ml and t, we can get three equations equating the indices on each factor from both sides. So if we start with L, since it's the first one that comes, on the left L has got just the index 1, but on the right you're going to get minus 3 alpha from the first factor, and you're going to get just beta from the second factor, and you're going to get gamma from the third factor. Now if we look at M, then we would get nothing on the left because no M appears, which means to say essentially that it's m to the power 0, just 1. And on the right, taking it term by term again, an alpha from the first one and nothing from the second and third. If we take t, then we get on the left minus 1, and from the right nothing from the first factor, minus 2 beta from the second, and nothing from the third factor. Well, ironically, the first equation there is the most complicated. Equations 2 and 3 give us immediate answers. Alpha is equal to 0, beta is equal to a half. So now if we go back to the one that was complicated, the first one, we're saying that 1 equals 0 plus a half plus gamma. Moment's thought tells us that gamma must be a half. So our formula up above really should read V is equal to K, ρ essentially to the 0, so we don't need to write that, g to the half, and lambda to the half. Now that's not the most helpful way of writing it, so if we look at a better answer, there we are. Alpha is 0, beta is a half, gamma is a half. That was our analysis, and the equation, or the formula, is written in a rather more convenient, more assimilable form using a square root sign. Well, that brings us to the end of this video, the third in the series on dimensional analysis. The next one is on modelling, and I hope to be with you later to explore that.